Good afternoon, everyone. Let me start with self-introduction. My name is Yuto Kawamura. I'm a senior software engineer at LINE. I joined as a new grad in 2015, and since then, I mainly did LINE messaging server development and HBase operation. And currently, I lead the team delivering the company-wide Kafka platform. Since I do a lot of Kafka-related work, I am also active in the open source community, and I contribute the codes. And also, just last month, I attended Kafka Summit in the United States, and I spoke at the conference. Thank you very much. So today I will talk about the company-wide Kafka platform that we operate at LINE. If you have attended Dev Day last year or before, at LINE we have HBase and Redis cluster, the large-scale middleware, distributed middleware, and Kafka is one of them. So, for those who don't know, Kafka is a software, and it is the middleware and its surrounding ecosystem for data streaming. So, there are several characteristics that it has for large-scale services. One is high availability and scalability. Second is that it supports data persistency. And once data is written on Kafka, it is persistent after that. And also, it can support data distribution in pub-sub model. So in understanding Kafka architecture, there are three components to be understood. So on the left-hand side, this is the producer. So producers are the clients writing data to Kafka. And in the middle, broker. And brokers are arbitrary number of nodes. And it can host an arbitrary number of topics. That is the unit of data management. And producers would identify the topic and can send data. On the right-hand side, consumers who are clients that read data from Kafka, they specify the topic to read data. So for one topic, there might be multiple consumers that can exist for several different purposes. So once one topic is written, it can be read multiple times by different consumers. This is the pub-sub model. So at LINE, we have a large-scale Kafka cluster. So it is not just for specific service or system, but it can be used as a generic platform for many services and systems. So in LINE server development team, firstly, in order to simplify the server architecture, it was implemented as the intermediate layer. And after the success and high reliability, other teams also wanted to use it. Therefore, now it has developed into a company-wide platform. At LINE, there are two purposes in using Kafka. The first is simply as a distributed queuing system. For example, in one service, we may have a web application server handling a very heavy processing. So instead, in the background, there might be task processor, and we can use this queue to request this processor. Another is a data hub usage. So data update from one service and to other services, we can use data hub, Kafka as the data hub to distribute the data. So at LINE, we have the friend relationship data of users. So user A may add user B as a friend. And in LINE, we have the necessary processing for that. In addition, this relationship update is handled as event. It is written as a topic to Kafka. And this event that is written here is used by statistics system and also as user graphs for timeline and other services. And if you are using Line, sometimes you may have unknown friends being added and them sending you spam or ads. You may have had such unpleasant experience. So we would analyze such undesired user activity to detect and to penalize them. And such systems also use this event data. What is important is that in one large Kafka cluster, it has to be shared by multiple services and systems. And there are two reasons for this. One is that there is the concept of data hub. So intentionally, we want to centralize large data on one cluster so that services that can use the data can discover the data easily, and in a unified way, they can access the data so that the architecture can be kept simple. Another reason is that we can make the operation more efficient. If all the services and systems require Kafka cluster each, then our operational cost would grow in proportion to the number of services we must support. In order to avoid that, we use one cluster so that our engineering resources can be concentrated on that small number of clusters, and we can maintain reliability and performance. Therefore, we have many services in Line which are dependent on a Kafka platform. Line, of course, as well as blockchain and ads platform, and live service, and data analytics, and timeline service. And there are many other services using Kafka platform as their backend. As a result, our cluster is very large in traffic. On a daily basis, 250 billion messages are written. And also, regarding data volume, it is 210 terabytes at peak, 4 gigabytes per sec. That is the data written. And there are 50 independent services and systems using the cluster. As a single cluster, this is the world's largest scale. Our Kafka cluster is used as the backend for many services. Therefore, the reliability and performance required are very high. And to these requirements, we need to meet the requirements with multi-tenancy operation, and there are some conditions required. The first is that the cluster itself has to protect itself from abusive clients. Our platform is provided for internal systems and services, so we do not expect there to be any malicious attacks. However, for example, there might be misconfiguration or mistakes in deployment, and we may have unexpected workload coming to the cluster. Moreover, which cluster is coming from which client, we need to be able to track that so that if there is any unexpected resource activity on the cluster, we can identify the client causing it to solve the issue. Lastly, we need isolation on the workload to a certain level between the clients. For example, one client, due to its workload, may have slow response time. For the same reason, if unrelated clients connected to the same client experience such response time, that is not desirable. And second requirement is to protect cluster from unexpected workload. From our experience, we know that in operating Kafka cluster, rather than the data size, what's important is the number of requests. And Kafka is well designed for that. For example, Kafka doesn't have its cache layer Instead, it uses the page caching that is held by the operating system so that large data is not duplicated on the page cache and its own cache. And also, there is native support for batching. So multiple records can be merged into one record to be sent to the cluster so that the data volume and request number may increase, but the overhead per request can be minimized. So for us, requests, the number of requests coming from the clients must be managed. Therefore, we are using the feature of request quota for Kafka. So broker resources to be used by a client, more specifically, the broker's thread time can be limited. And for each client, we can set the limit on each cluster as a default so that the resource volume can be limited. So if one client goes out of control and sends requests to the Kafka, the cluster overall will not go down or will not degrade in performance. Another requirement is workload isolation between clients. For this, in our production environment, the trouble that we have seen in the production environment and how we have solved them. Let me introduce some examples. Regarding the identification of issue, so that was done by the worsening of response time on a cluster. Produce request when writing the data, this produce API, the 99 percentile response time was worsened by 50 or 100 times compared to normal time. We did some investigation and we discovered two things. One is that in that time, on broker machine, there were many disk reads. Another discovery we made is that the network's thread, which is the I/O thread between clients, the utilization of the thread was very high. So we did investigation on this issue. But before that, I would like to explain how Kafka handles requests. Kafka request handling is made of two thread layers. The first layer is network thread. So this is the thread for handling IOs between clients. So reading the request coming from client socket, it prepares the response and writes that to the socket. Another layer is request handler thread. So the request read by network thread is processed and it would prepare the necessary response object and returns it. So this is the overall flow. So request comes to the socket, and network thread would read the request and creates the request object. And that is written into request queue. Request queue is prepared only as one queue in the broker. And all of the request handler thread would call this queue to obtain the request. So one request handler thread is it takes out the request and it is processed. And then there is I/O to the local disk and response object is created. The response object is written to the response queue. This response queue is prepared for each network thread so that, going back one slide. So, response written in the response queue is only processed by the network thread that is in charge of that. So network thread would take out the response object from the queue and then writes that to the client socket, and that completes the process.
So what it means is that network threads has conducts event loops thread, and up until now we were using the event-driven asynchronous I/O. So if there's several, it sort of multiplexes several sockets, and then it sort of consecutively makes a processing, and that's what network threading is. So basically, network thread within whatever that's processing that's going on, depending on the I/O, it doesn't get blocked by the I/O. So in some connection, when it's made, that connection within the broker, within the several threads it gets assigned to, and one of the networks, it only gets processed by one network thread. So what we've been sort of checking into is the network thread utilization was increasing, and what kind of a case does this happen? We thought about that, and one of the cases is that whatever that has to be processed, the number of requests that are increasing, and if we're busy, that's one of the reasons. But when we look at the metrics, if there are no changes in the metrics, we check that. So we thought about other possibilities. Another possibility is that the network thread was processing within the event loop. In some processing, there was a blocking that was going on, and so because of that, the thread's utilization was increasing. That was one of the possibilities. So when does this happen? And so to understand that, we looked at the Kafka source code, and as a result, one of the reasons this was occurring, we understood. And to understand that, we had to look at the API's response processing, the differences between that. We had to understand the differences in the processing. The fetch API and the other APIs, there was a difference in the processing method. And what I need to talk about is other APIs. And the other API's response processing, the response queue to response objects network, it was sort of acquired by network thread. Whatever data that's written by the network thread is all prepared. So on the network thread, one of the things to do, this prepared data, is to copy the socket. That was one of the operations. But the fetch API, this fetch API is a little bit different. The consumer, when it gets the consumer from the cluster, that's the API. So the topics data is to try to read the API data. And so in that sense, in the broker is when they return the response, whatever topic that's stored on the data, it copies on the client socket. And that process, the broker uses a system called send file, and the send file system call is in the Linux. It's available in the Linux. It's a system call available in the Linux. In the local disk data, it sort of directly copies, and that's the API that makes it possible. And depending on that, the user space's memories, if the memory is copied once, so we can prevent the overhead. And so it's extremely efficient, and that's what we found out. And the Kafka, design-wise, is very dependent on this feature. But because it's targeted data, if it's on the page cache in the Linux-related issue, that it copies the Linux API. But if the page cache doesn't exist, then from the local disk, it has to load the data. That's the necessity. So from this disk load is happening, what happens? So we thought about that too. So on the targeted data, it doesn't exist in the page cache, or it exists in the page cache, and that's a simple memory operation, copying operation. Typically, there are several hundred milliseconds or several hundreds of microseconds that can be processed and concluded, and that's what's known. If, on the other hand, if the targeted data has to be read from the data, then that slows down the speed. Typically, it takes like several milliseconds to several tens of milliseconds. That's how long it would take. So if this process is happening within the event loop, then that becomes a huge problem. So to verify this scenario, to further find out, we tried to find out the processing time of the send find system call. And to conduct this investigation, what we often use is a system tap. And the system tap is a dynamic tracing tool. It's one of the tools. And it was just by writing several scripts, then we can understand what's happening in the curl. We can detect it. And that's one of the tools. And as a simple rule, what we can see on the right side is on one of the machines, the system call is to count. It's a script that counts the system calls. And to simply put it, on the second line, there's a global CNT. It's a declared variable. And under the block underneath, whenever the system call is called, we increment it. And in the very end, at the very last block, we iterate the CNT variables, and we try to print out the number of time has been called. And as you can see, the number of the system call, the number of time it has been called, we can clearly see now. And so the system tap is very important. And when we deal with this kind of scalability, it becomes very important. And it offers a lot of low overhead. So in the production environment, we don't have to worry about the overhead. And we can just safely conduct our processing. And as a parity tool, there's DT trace or BPF is also known. And the system, by using the system tap, whatever that's been issued by the broker, the system call, the send file system call, we looked at the processing time and we made a calculation. And the script's details we're going to sort of skip, but what we got is a histogram. And as you can see, most of the processing time took from several milliseconds, and it was able to complete the processing in a short time. Only a portion of it showed a very slow processing time, but only a portion of it, so it's very short. So depending on that, what we found out was that we were able to make a hypothesis from this. If the broker, processes a fetch request, and at that process, if the send file to call the send file within that process, the disk needs to read the disk, and depending on the network thread, gets blocked by the event loop. And in that sense, whatever that's being processed underneath, not only that, but only the same network, whatever that has to be processed later responses to, everything gets blocked. So depending on this, the latency occurring by the disk read, all the responses that are waiting, it causes a wait. And whatever that's unrelated, the workload isolation was broken, and it sort of aggravated the wait time. And to solve this, what we needed to do, we thought of many ideas, and what we sort of arrived at the very end is whatever that's not supposed to be, event loop that's not supposed to be blocked, we try to fix it so it won't be blocked. And in order to do that, the send file on the network thread, at the point of being called, the targeted file has to be loaded onto the page cache. That's the improvement that we try to implement into the broker. And as an idea, the current blocking behavior, within the network thread, we try to load the data through the request handler, and we try to switch it to the request handler side. And the request handler thread, for single queuing, it pulls for single queuing. So the blocking here didn't affect the other blocking, and the other threads was able to sort of continuously do the processing in the end. So there was no more blocking on the single sort of queues. So what was warmed up, the page cache that was warmed up was read again, and it was written out in the client again, but this blocking didn't happen here. So the page cache, to warm up the page cache, we had to do the processing. And how we're going to conduct that, so I have to think about this a little bit. So the simplest way to the targeted data, we had to do the reading. That's one of the ways of doing it. But in that sense, there is a concern for this method. And if the targeted data if it simply reads it, then that data gets loaded by the disk. Then the user space buffer, it gets copied to the user space's buffer. And in the end, why does Kafka use send file anyway? Why does it use a system call anyway? And it's because it wants to prevent the massive memory copy to the user RAM. And in this way, then whatever the Kafka that has the efficient performance characteristic gets sort of lost. So I had to think about the other methods we could use. And after thinking through, it was a little bit tricky, but we came to a sort of solution. And for the targeted data, we're going to call the send file. But at that time, the address, we're going to set it to dev null for the address. And in the Linux-related implementation, the send file is dev null's destination at that time. Then the memory copy is not done not at all. We found that out. So from the disk page cache, when we load it, it's going to be loaded, but the memory copy after that will not be conducted. For us, it was a very ideal sort of execution. So this behavior was very interesting, so we tried to find out more, and we tried to look at the internal implementation of the Linux kernel. And I'm not going to get into any details, but to simply put it, the send files API is a Linux internal, is mapped by a splice called implementation called splice. And the splice is for each device driver has an implementation. So, and here, what we show here is a null device, is a device driver. As you can see, the splice right null function is internally is pipe to null. It calls a function called pipe to null. And within the function, the memory copy doesn't happen at all. That's what we found out, or you can find out from here. And because of that, we were able to get a confirmation. And this, from the page cache warm-up, this processing, when we try to implement it to the broker, we have to do that. And as a way of doing it, it's very simple. And we have to do a prepare for read page cache warm-up. We just took it out, and then, but what we're doing is we're just opening the file to dev null, and the file channel is transferred to, we're calling the method. That's all we're doing. And the Java standard library, the file channel, this class is transferred to has a transfer to method function, and if it's internally usable, then we just it's implemented to use send file. So we use a, we didn't have to use a JNI, which was fixed to a platform, and we can just implement it by Java's code. And we actually deployed this to our production system, and as a result, the problem was completely solved. And as you can see, and the problem was the discrete disk read from the whatever that was processing the fetch read. In that process, the unrelated API response time, there was no effect to that. There's no impact to that, as you can see. And as you can see, in such when we performed this, we wanted to return this to open source. That's what we do often. And in this case, this time it's not an exception. In this, we already had a ticket in upstream, and currently it's under discussion. But if this gets merged, then the cache's tail latency will be 100 times, or 10 to 100 times will be reduced. So other than that, we're also conducting a lot of performance improvements, and Kafka has made a lot of contribution. And through this activity, we want to sort of contribute to the worldwide Kafka users. If you're interested in more details, these are issues ID. If you look for the issues ID, you can get the upstream ticket. You can take a look at it. So please take a look at it if you're interested. So I want to conclude here. So today we talked about inline, so the Kafka platform that's used across the company, and what we're doing, what kind of engineering we're conducting. That's what I talked about. And Kafka's quotas feature or system taps tool. By using these, we solve the problems, and to understand the patch that we understand the system deeply, and we sort of, by solving a lot of the problems, our systems policy is going smoothly, I think. And the data hub as a concept, by maintaining the data hub concept, supportive service and other operational costs, and by not proportionally increasing, we are more sort of efficiently maintaining the platform. And whatever that's occurring, the performance improvements, achievements, we are actually contributing back to the open source community, and to all the worldwide Kafka users, we're making the contribution. And so through this talk today, what we're doing today, the engineering that we're doing today, what kind of engineering we do, if some of you can understand that, I'll be really grateful. In the end, so I want to talk about sort of some of the future prospects. And from the 2 points I want to talk. And one is that from the Kafka's platform itself is going to keep evolving. And right now, we have a lot of issues, but one of the biggest issues is that the client's standardization and the maintenance is one of the big issues. And currently, our platform, by using a lot of the clients that use their platforms, has various frameworks and various Kafka versions, and that's one of the issues that's been created. And because of that, what we want to do is, if you want to support a client, at that time, there's the various sort of issues. It becomes inefficient or increases the complexities. And within our team, currently, internally speaking, what we're using internally, the efficient consumer framework, that's what we're trying to develop, and the client's SDK's development, that's what we're trying to do. And through that, we want to sort of standardize the client, and in the end, we want to make it more easy for us to manage. That's what we're trying to achieve. And in the end, and to achieve higher availability, that's more important for us too. And our platform is recently, we were able to experience a huge outage, and we were able to see a lot of issues from this. It left a lot of issues to be resolved in the end. So continuously, we want to conduct engineering to make availability more available. And another axis is that SRE team. We're going to be building an SRE team, a new SRE team, and this is currently the middleware or for each service, the various teams that are conducted, sort of the reliability engineering or performance engineering, they're conducted in various teams. And within that, if there's especially operating systems levels, knowledge, or specified softwares, sort of tools that are not dependent on frameworks, if we can go across different team departments, and as an across the board, if we can increase the service reliability, that's kind of the plan that I'm talking about. And if you're interested in such domains, or I'll be in the Ask the Speaker in the cafe. So if you can come over and we can talk and we can have more conversation, I think that'll be more stimulating. That'll be it for me. Thank you very much for listening.